Alright, in the previous video, we explored several traditional control methods. Most of those controllers rely on a mathematical model of the system. If we know the physics reasonably well, we can design a controller that performs very well. But in many real engineering problems, that's not the case. A robot may pick up objects with unknown weights. A drone may suddenly experience wind gusts. A vehicle may drive on a dry asphalt one moment and on ice the next. In this situation, the controller must deal with uncertainty. Instead of assuming we know everything about the system, modern controllers try to estimate unknown dynamics, adapt their parameters, learn from data, or even learn directly by interacting with the environment. In this video, we are going to look at 5 important data-driven and AI-based control methods. We will start with active disturbance rejection control, or ADRC. Let's imagine we have a motor driving a mechanical load. We may know the basic dynamics of the motor, but there are always things we don't know. Friction changes over time, external disturbances may appear, the plate might suddenly become heavier, or perhaps our mathematical model is simply not perfect. Traditional controllers try to model these effects as accurately as possible. ADRC takes a completely different approach. Instead of modeling every uncertainty separately, it treats all unknown effects as one total disturbance. The main component in ADRC is the extended state observer. This observer continuously receives information from the system. Using the measured output and the system behavior, it estimates not only the system states, but also the unknown disturbances acting on the planet. Once the disturbance has been estimated, the controller immediately compensates for it. In other words, instead of waiting for the disturbance to affect the output, ADRC predicts its influence and actively rejects it. That's exactly where the name comes from, active disturbance rejection control. The main advantage is robustness. Even if the mathematical model isn't perfect, ADRC can still achieve excellent tracking performance because it continuously estimates and compensates for uncertainties. Now let's move to another adaptive control, Model Reference Adaptive Control, or MRAC. The basic idea here is actually very elegant. Instead of trying to make the planet follow reference signal directly, we first define how we wish the system behaved. This is called the reference model. Think of it as the ideal response. Maybe we want the system to settle within 2 seconds with almost no overshoot. The reference model produces exactly that behavior. Meanwhile, the actual system responds accordingly to its own dynamics. If the planet behaves differently from the reference model, an error is generated. This error is sent to the adaptation mechanism. The adaptation mechanism continuously updates the controller parameters until the planet behaves almost exactly like the reference model. So, unlike ADRC, which estimates disturbances, MRAC continuously updates the controller itself. The controller literally learns how to imitate the desired model while the system is operating. Alright, suppose we don't even know what the best controller parameters are. All we know is that we would like to maximize some performance measure, maybe fuel efficiency, maybe braking force, or perhaps energy efficiency. This is where Extremum seeking control becomes useful. Instead of relying on a mathematical model, this controller performs a very small experiment. It slightly perturbs the control input and observes what happens. If performance improves, it keeps moving in that direction. If performance gets worse, it moves in the opposite direction. By repeating this process continuously, the controller clips toward the optimal operating point. You can think of it as searching for the peak of a hill while blindfolded. Uh, it doesn't know where the maximum is. It simply keeps testing and adjusting until it reaches the optimum. Up to this point, every controller we've discussed has relied on mathematics in one way or another. Fuzzy logic takes a very different approach. Instead of equations, it uses human reasoning. Imagine driving a car. You don't calculate different equations. You simply think if the vehicle is going a little too fast, brake gently. If it's going much too fast, brake harder. That's exactly how a fuzzy controller works. First, crisp numerical values are converted into fuzzy sets. This process is called fuzzification. Then, a collection of human readable rules is evaluated. Things like if temperature is high, reduce power, or if speed is low and error is small, increase acceleration. Finally, these fuzzy decisions are converted back into the precise numerical control signal. This final step is called defuzzification. Fuzzy controllers are especially useful when expert knowledge exists, but developing an accurate mathematical model is difficult. Finally, let's talk about one of the most exciting topics in modern control, reinforcement learning. Unlike the previous controllers, reinforcement learning doesn't begin with predefined equations or expert rules. Instead, it learns by interacting with the environment. The controller, which we call the agent, observes the current state of the system. Based on those observations, it chooses an action using its policy. That action changes the environment. The environment then returns a reward indicating whether the action was good or bad. Over thousands or even millions of interactions, the agent gradually improves its policy. Eventually, it learns which actions maximize the long-term reward. This is why reinforcement learning has become so popular in robotics, autonomous driving, industrial automations, and even game playing. Rather than programming the solution explicitly, we allow the controller to discover it through experience. We've now explored five very different approaches to intelligent control. Although they all aim to improve system performance, each one follow a completely different philosophy. ADRC estimates and rejects disturbances. MRAC adapts the controller to match a desired model. Extremum seeking searches for the best operating point. Fuzzy logic mimics human reasoning through rules, and reinforcement learning learns directly from interaction with the environment. So, thanks for your watching. See you next time.